Let's look at circuit number 2 now. It is a half-wave rectifier, and we are being told that it has a 100-volt amplitude 50 Hertz sine wave that's driving it. The diode that is the rectifier is a 1N4148, and we have a 1 kilo ohm load. The capacitance is 20 milliseconds divided by R1, and then 200 milliseconds divided by R1. So let's look at the first case. 20 milliseconds divided by R1 would be 20 millis divided by 1,000. That's 20 micro. We're also given the model for the 1N4148. So let's go back here, and since I got that model, let me go ahead and drop it in here. We just put it down below our circuit net list. So our voltage source is a sine wave, and if you don't recall how to specify a sine wave, then pull up the PSpice ref, and let's go to analog devices, voltage controlled, independent voltage sources, which directs us to independent current sources because they're the same form. And then let's look for, let's see, we have these different types of waveforms. We're looking for the sine wave. So let's keep going until we find sine wave. Ooh, that's a loud refrigerator. There we go, sine wave. So we specify the offset, the amplitude, then the frequency. There are additional 3 parameters that we won't need to specify. They're optional. One is delay, if you want to start it after a certain time. Some damping factors, so that if you want an exponentially decaying amplitude, and then you can set the phase. So we won't need that. So offset is going to be 0. First it's sine wave, then it's 0 volts offset, 100 volt amplitude, and the frequency of 50 Hertz. And that's that. Let's go to our circuit. Okay, then we have D1 going from pin 1 to pin, I guess that's O for output, and that's a 1N4148. This value here, Spice will look for a model for it, so we have to have a dot model, or you can also do a dot, like an include, that includes a library file that has the model. But the way we're doing it now is we're specifying our own models. C1 goes from the output O to ground, and it has a value of, what do we say, 20 microfarad. And then, and I don't know if this is necessary. I'm going to go ahead and put an IC equal to 0. I don't think that was requested. And then R1 from O to 0, and that was, what, 1K? 1K. Okay, I'll go ahead and take this initial condition off because it wasn't asked for. Okay, so we have a dot model. Again, the syntax for specifying a model is dot model, and then the name that you make up, could be any name. The type of device, so if it's a diode, it has to be D. If it's an N-channel MOSFET, then it's NMOS. If it's a resistor, it's R, etc. And then parameters that are associated with it. So I'm just listing 3 parameters, ones that we talked about when we covered diodes in class. Simulation time, well, let's think about how long we want to run this. If we're doing 50 Hertz, 50 Hertz is 50 cycles a second, that's 20 milliseconds. So if we did 100 milliseconds, that would be 5 full cycles. So let's try that. And for a time constant, let's leave the step off for right now. Go ahead and save that, and then let's run it. And we want to look at VO. Ooh, and let's look at VI, V1. All right, and we notice that if I zoom in, this sinusoidal waveform is kind of choppy. The reason for that is that the simulator is taking too big of time steps. So here we do want to, if you see something like this, you want to increase this, or specify the time step and limit it. So let's go ahead and say, let's say since it's 10 milliseconds per half cycle, and we want to say at least 10 points within a half cycle, that'd be a 1 millisecond maximum step. So let's try that. That looks a lot better. All right, then I'm going to go ahead and add a y-axis. I'm interested in looking at some current here. ID1. Ooh, now that does not look so good. Why is that so oscillatory? I'll limit this to go to 40 here. That should not be oscillatory. This is an indication to me that the time step is still too small. And you might go, how in the world do you know that? Well, I look at the circuit, and this to me looks like some kind of oscillation. But I look at the circuit and I say there's no inductor and capacitor in here. There's no way that it can oscillate. Maybe if V1 had some harmonics or some waveform in it that was changing at the rate that this blue signal is, then I could see where that kind of oscillation is coming from. But because there is no such thing in this circuit, I have to conclude that there's some artifact there, and it actually is a result of the simulator taking too big of steps. And so let's shorten this significantly. I'm going to go from 1,000 microseconds to 20. That's a factor of 50. And let's see what happens. Ah, there we go. That's much, much better. You now see a nice continuous current. Let's go to 60. There we go. All right, now let's look at what we're asked to measure. For circuit 2, what is the load resistor R1's peak-to-peak voltage when R1C1 is equal to 1/50th and when it's 1/5? So you're going to need to run the simulation twice with two different values of capacitance, but essentially all you have to do is pick off the peak-to-peak value of channel or of trace VO, all right, which again in the probe video I showed a couple different ways to measure that. This is the least effective way, least precise way, but I just wanted to rough it out here. It's roughly 55 volts. All right, I think I'll stop here for circuit 2 and we'll move on to circuit 3.